Okay, so 3.6, this is talking about linear pairs and vertical angles. I mentioned vertical angles yesterday. We kind of talked about what they were briefly. This is more of a, we are going into it solidly what we're going to do. Okay, so what they're trying to get you to do is just define what these are and then learn about what are some of the things about measures that go along with these. Okay, so a linear pair of angles is basically when the combined pair makes a line. Okay, so in this case, it doesn't matter where I put this, but you have a line with one ray. So it's a line with one or more rays, I could say, but a linear pair is just one ray. Okay, so this is a linear pair. Pair is two, they are on a straight line. Notice that it makes a straight line. So here's my line. I could label this line AC. Remember when I make my notations, it's AC like that represents the line. Okay. I'm going to name this one right here D, and I'm going to name the vertex B. Remember, the vertex is where all the rays come together for those angles. Okay. So in this case, I have two angles. I'm going to label this one 1 and this one 2. Okay. That is one way. If you don't like to name angles with a bunch of letters, you can actually put in just a little thing and name it by a number. Then you can refer to this angle as angle 1 and this angle as angle 2. But notice it has to show you where that angle is. It gets confusing if you make a big line across the whole thing, because that gets more confusing. So I would only do it on the separate angles. Don't do it where you take 2 or 3 or 4 angles and put them together. Okay. So here we know that angle 1 and angle 2 are on this linear pair. What do you know about angle 1 and angle 2? They form a line, so what do we know about them? Yes?
They add up to 180 degrees.
They add up to 180 degrees. So if I add these together, they equal 180 degrees. That will be used throughout our work in geometry. Okay, this is such a basic principle. Look for lines. Look for lines. If you see two angles on it, they must equal 180 degrees. Okay, this is going to be used all the way through as we look at different shapes, different figures, all that kind of stuff. You will be using that basic fact. Okay. What are those two angles called if they add up to 180 degrees? We talked about this yesterday. Yes?
Supplementary.
That's right. Correct. They are supplementary. Supplementary is how I usually say it, but if you're doing it phonetically, that is correct what you just said. Okay? So those are supplementary, which means basically if the two add up to 180, they're called supplementary angles. That was what we talked about yesterday. So that's where we're looking at it. Okay? So that's a linear pair of angles. We see those all over the place. Okay? So if I knew what angle 2 is, I could find what angle 1 is by subtracting. Okay? So that's kind of what you can do on that. Okay, vertical angles. They are formed by two intersecting lines. That means they're concurrent. Remember that big word concurrent? The lines, if they go through the point, they are concurrent. So vertical angles are like this. I have one line here and another line here, okay? They intersect. Okay, you see where they intersect? Okay, so here we have this line, which is line A. We'll put B, C. This is D, B, E. So I labeled all those points on there. Okay. So I have line AC. Again, I'm just getting you used to the notation. Intersect line DE at point B. So that's what we can say. We have AC, which is this line, intersecting DE at point B. Okay? So that's all it's telling us. They intersect at point B. Then the vertical angles are the angles opposite of each other. You actually get two pairs of vertical angles. Okay, if I look at these, which two look like they're the same size? Okay, let's put some numbers on. I'm going to call this angle 1, this angle 2, this angle 3, this angle 4. Okay, looking at these, there's two pairs that are equal. What's one pair that looks equal just by looking at it? Yeah, Paxton.
2 and 4.
2 and 4 look equal. Okay, so these are called vertical angles. Okay, they are the opposite angles when they're formed this way. So angle 2 and angle 4 are vertical. Because they're vertical, then angle 2 is congruent to angle 4. That means they have the same measure. Okay, that's what that really tells us. Okay. Now, there's another pair. What are the other pair? Yes. Go ahead.
3.
1 and 3. So we also know that angle 1 and angle 3 are vertical. So you get two pairs when you're doing this. So angle 1 is congruent to angle 4. No, how about 1 and 3 are congruent? And angle 1 and angle 3 have the same measure. Okay, so that's the basic definition. So you have to have bisecting lines. The opposite angles in these bisecting lines are called vertical angles. Okay, they have the same measure. It looks like they have the same measure, and that is true. They do have the same measure. Okay, so that's what we're looking at here. Okay. Let's see. Now that's what they gave you. Okay, so let's just look at a pair. Here we go. That's an interesting question. Let me see. In the circuit O on ON and OA. OA is 50. Okay, let's see what we can find from these. Let's do a problem here. Okay, so this is our picture. I want to make sure it has that. Yes, it does. And then it goes like this. And like this. So ON is centered at point 0, and the coordinate ON is 0. So this is N. A, to go around, see. E, B, S, D, this is W, and this is AB, ABD. Yep, okay, C. Okay, do you notice that we have N, E, S, and W? What do you think those stand for? Yes.
Northeast, southwest.
Yeah, those are directional signs, northeast, southwest, okay? That means, what kind of angle is this? What kind of angle is formed right here? Between WE, line WE, and line NS. Okay, so you have NS, and we have WE. What kind of triangles are formed right there?
Right.
Yeah, they're right triangles. All of these are right triangles. So when we have a north, south, east, west, they are considered at right angles, okay? So these we know already are 90 degrees. Okay, that's what we know. We know those are each 90 degrees. Okay, so always kind of pull out, we know that these are 90 degrees in each corner, okay, is 90 degrees. So pull out if you need to see that. Yes?
So each like angle's 45.
Well, I didn't say I bisected.
Uh,
Okay, so you can't do that, but I could draw this to show that these are, so if I put a square around like that, it just says those big ones are 90 degrees, okay? So that's all that's showing. I like to pull it out so I can see it, because sometimes looking at that, it's kind of a mess, okay? So I like to pull it out, but you can use a different color and do that. It says that this line, or this one we measure, it's at 0 degrees, and this one's at 50 degrees. So can I find, I'm going to give you numbers to these. Let's call this angle 1, angle 2, angle 3, angle 4, angle 5, angle 6, angle 7, angle 8. I tend to like to use little things with numbers because it's so much easier than naming all of my angles. Okay, yes?
Wouldn't half a 90-degree angle be like 45?
But did I say I bisected it? No.
No.
So I did give you what the measurements were. If this is our 0 on our protractor, we get 50 right here. Okay? So what is the size of angle A, or angle 1?
50 degrees.
50 degrees, because from 0 to 50 is 50 degrees. So this one is 50. Okay? How much is angle 2 and why? Yes,
40.
it's 40. Why?
Because it's a right angle.
Because it's a right angle, so this one plus this one must equal 90. So this is 40 degrees. Okay? Now, can I find angle 6? What is angle 6 and why?
Oh, it's 40.
It's 40. Why?
Because it's vertical.
It's a vertical angle. If you look at this one and this one, they're vertical angles of each other. So angle 6 is also 40 degrees. Okay? What is angle 5?
50 degrees.
50 degrees. Okay? So this one's 50 degrees. Now the question is, can I find 3 and 4 and 7 and 8? Three, 4, 7, 8. Hmm?
Maybe.
Do we have any information that really gives us that? We know that this is 50 degrees. We don't really know what this is, do we? We would actually need to have one more protractor measure to get this. So then we could say, okay, well, I found this one is at, let's see, that's 50, 100, or 90, this is 145. Okay, so if it's at 145, what is the size of 3?
55.
How do you know that?
Because you were already at 90
Okay.
at east.
Okay, so this is already at 90. So this would be 145. So from here to here, this is what we've been doing with those betweenness things. From here to here, it has to be 55 degrees. Now I think we can find 4, 7, and 8. What is 7 going to be? Yes.
35.
Ooh, look at 7. It's across.
Oh.
55.
I
Yeah,
was
yeah.
thinking of 4.
Oh, I know you were. That's why I jumped to 7, just to be stinker. Okay, Aaron, what is number 4? How much do these two equal? 3 and 4, how much do they equal?
At 90.
So if I have this one is 55, how much is this one going to be?
That would be 35.
35. And we have in one opposite of that, so it is also 35 degrees, okay? We have to know at least 2 angle measures on that. You know that this one's equal to this one, but you also have to get this one equal to this one. If I don't know the measures on here, it's not guaranteed that they're at the same angle as this 50 over here. It's not guaranteed that they are there. We have to have at least 2 measures to do that. Okay, so that's something that we're working on. So that's really the whole section 3.6. It's just looking for linear pairs. It's looking for vertical angles and finding measurements of those angles. Trying to get ourselves used to that, because you will be doing this a lot in the course of geometry. Okay, and there are things you need to be able to look for. Okay. So we're still just working with lines, rays. So if you think about our basic geometry so far, we have been working with points, lines, line segments, rays, and angles. Okay, that's really all we've been looking at. We haven't looked at any other type of figure, a square, or any of those. Okay, so that's what we're working with so far. Okay, so let's go now. We're going to do 3.7. 3.7. Okay, this is talking about perpendicular and parallel lines. Okay. Perpendicular. Okay, think about that word. From previous math courses, what do perpendicular lines, what are they made up of? Yes.
They look like this.
They're like this. What do they form?
A cross.
They form a cross. What else do they form?
4 right angles.
4 right angles, okay? So it's 2 lines that intersect at 90-degree angles, okay? So it's 2 lines that intersect at a point forming 4 right angles. Okay, so yes, the cross. How you indicate that a line is perpendicular, I think you just saw that earlier. You can just go like this. If you put the little squares in like that, that tells you all of those four angles are right. That's one way. The other way is you actually can just put it down in one spot. Okay, does anybody know why I only have to mark one? Why do I know this one's also 90 degrees? Yes.
Because if the one that, if that one wasn't 90 degrees, all the other ones would be off too.
They would be, but why can I say that one's 90? Yes.
Because the lines are straight.
Because the lines are straight. Remember, a line is 180 degrees. This one's 90, so that means this one has to be 90. Okay? Just because they're a linear pair. What is this to that? This one and this one are what? What kind of angles are they? They're vertical. And vertical angles have the same measure. So this one has to be 90. I could also say it's a linear pair with this one, and so it has to be 90. Now once that one's 90, I have a linear pair here, that one has to be 90, or I can say there's a linear pair here and that one's 90. So technically, I only have to put in one, and that will make all of the rest of them 90 degrees. So if you just see one little symbol in something in a drawing, that means they're still perpendicular. Because if two lines intersect and one angle is 90, then all are 90 degrees. Okay? So that's something to notice about perpendicular. We don't have to mark all four of them being right angles. Okay? We only have to mark one because that therefore implies all the rest are, because we're using straight lines, linear pairs, etc. to get those other measurements. Okay, so that's what a perpendicular lines are. Pretty easy, it's not too hard, that's how you look at them. Okay? Now we're going to go into parallel lines. Okay, somebody from previous math classes, what is a parallel line? Yes,
When two lines don't intersect.
that's correct. They never intersect. So it's two lines that never intersect. Okay? If I have a line like this and a line like this, what do I know about the distances between them? If I measure the distance between two lines that never intersect, what do I know about those distances? Yes?
They'll stay the same.
They'll stay the same. Okay, so the distance between the lines stays the same. Okay, question. Where do we see parallel lines in our world? Yes?
Railroad tracks?
Railroad tracks are exactly parallel lines, because otherwise the train wouldn't fit on it, because they do not change the distance of their, what is that called? Their wheels? I guess they're called wheels on a train. Okay. The wheels don't change place. They don't get bigger apart, closer together. You have to have parallel lines. Where's another place you see parallel lines? Yes.
Power lines?
Power lines can be parallel. Usually when we do them from one to the next, why do we want them parallel? Come on, somebody else answer besides Micah. Come on, somebody else. Why do we want, yes, David.
You don't want the lines to cross,
Why?
they'll like explode.
Yeah, there's a chance they'll short each other out or cause an explosion. We don't want lines to intersect when they're power lines because it causes all sorts of explosions, you know, all sorts of fireworks, all that kind of stuff when we have them cross together. Yes.
Also, like, the sides of the door frame.
Sure, the sides of a door frame are usually parallel. Okay? Why? Why do you think? Lucas, why do you think door frames are parallel?
So the door closes.
Why? Why does it have to be parallel?
So the door fits.
So the door fits. What is our door usually made up of? It's a rectangle, right? And rectangles have parallel lines. We have to keep them the same distance apart. Okay? Okay, another place you might see parallel lines. How many of you, just a minute, how many of you guys watch football? Okay, so those people, Aaron, is there anything on the field that would represent parallel lines?
All the lines on the field.
All the lines on the field. Why? Why are they parallel? Yes.
Because most of the lines mark distances or boundaries.
Yes.
So if any of those were like, if they weren't parallel, like it would start like on this side of the field and on the other side of the field, it would be like not where it's supposed to be.
Yeah, we are measuring
That'd be
distances down the field. And specifically, it's because we are measuring the same distance, we want to represent the same distance for each of those lines. That is why we have parallel lines on the football field. Okay, so there's all sorts of places parallel lines can be seen. A road usually has parallel lines. Now, I do know the size of a road can change, okay? But for the most part, it has to be at least so far apart or our cars won't fit. Okay, so that's where if you look down a road, you will see parallel lines. Okay, so that's another place that you can see them. Okay, perpendicular lines. Think about where do you see perpendicular lines in the world? Yes?
Four-way intersection.
A four-way intersection, beautiful. Usually most intersections come and they come together at perpendicular lines. Not all of them. There's a few that don't, but most of them at intersections are, okay. I think we need to stop entertaining one another and just listen to what's going on. Thank you. Okay, so at an intersection, that's an obvious perpendicular. Where's another perpendicular anybody can think of? Where else do we see perpendicular lines? Okay, look in the corner of this building. Look in each corner of the room. A parking lot can have perpendicular lines, okay? But just think about here. Look at the corners. What are those?
Perpendicular lines.
They're perpendicular lines. Now, we don't see the top of the one above it, but if it's got another, when you're building this, these would definitely be at perpendicular lines because it's the only way to keep our building square. We have to have perpendicular lines or it won't be square, okay? And we don't want a tilted, well, maybe somebody wants a tilted one. The Leaning Tower of Pisa, which is over in Italy, is not actually crooked. It's crooked not because it was built crooked, it's crooked because one side sank. So the actual building is, when you go up on it, if you set it upright, it would be perpendicular. But because it's tilting, because it's sank on one side, it's tilting. Okay, yes?
It's actually, it is crooked. They try to compensate for the lean, so it's actually built up more on one side.
Oh, okay. Okay, so what he's saying is after it started going down,
During construction.
yeah. Oh, well, whenever it starts sinking, they tried to compensate for that, so it actually isn't perpendicular, but it's mainly caused by the sinkage, okay? It's quite an interesting place to visit. I've walked up the Leaning Tower of Pisa. It does give you a weird feeling because as you're going around it, you're going to one side or to the other, down, And so you climb up in a circular way, so you're kind of going down, then back up, then down, then back. It's kind of weird as you're walking it. You're not level. You're off to one side. Okay. Okay, that should be good, some perpendicular. Just think about things when you're going around, because we are measuring things of the earth, okay? Can you think of any natural things that are perpendicular? Yes.
Sometimes a tree branch.
A tree branch can be perpendicular, yes. Depending on the tree, they may have perpendicular branches that come out. Okay, does that remind you of any, well, we talked about that, the power lines, so they are perpendicular. What else? Anything else you see in nature that might be perpendicular? Okay, I think of really steep cliffs. You have the flat thing here, then you have the cliff going down. Sometimes it's it's straight down, okay? And so then you've really got this implied perpendicularness here, because if I extended that line up and that line over, it's at a 90-degree angle. And there are cliffs that are strictly at a 90-degree angle. You look down and it's straight down, okay? Those are the ones you don't want to accidentally step over, okay? Because that's not good for you. Okay, those are things I can think of. You know, just think of things around you. It's kind of fun to think about where we can find these different lines. Okay, so now that we know what they are, kind of where we see them, right, let's look at how we can use some stuff. Okay. Okay, I guess they don't really go into more of that. Okay, so let's go to this one. If light travels, so we're looking at number 1, the question number 1 for on page 119. So go to page 119. Okay, so if you look at this, it's kind of interesting. This is true. So if you have some water here, when sunshine hits the water, okay, when it comes in and it hits the water, some of it goes back up and some of it goes down. Okay, that's what happens when sunshine. So if you're ever around water, notice there's a reflection off the water. You feel the light back up on you, but some of it goes down so you can see down in the water. So sunshine comes down. This actually is what happens. Okay. Some is, it's called reflected and refracted. So this is reflected. This is called refracted. It's kind of fractured. It actually doesn't go down the same amount, or it could go down more depending on, oops. There, we'll go like that. Maybe I'll go like this. Here's our sunshine coming down, okay? So this ray is reflected up, this one's refracted down, okay? So they draw some different numbers in here. They have 1, 2, 3, 4. Oh, that's not right. What else did they have in there? 1, 2. Oh, they have the northwest, they have the perpendicular. So we're doing our, in here, this is our up, this is down, straight down, this is to the west, and this is to the east, this is to the west. So basically we know that's a right triangle, okay? So you have this imaginary perpendicular line. Something that goes straight down into the water and straight up towards the sun. Okay. You have these, which your water is usually flat, so that would be going east and west. Okay. So we know that this this angle right here is right. We know that these lines are perpendicular to each other because That's how we've made them. Okay. And it is true, they are right angles, they are perpendicular to each other. If you look at a horizon, you can actually kind of imagine a perpendicular line that goes through that. Okay, so then they label the numbers this way: 1, 2, 3, 4, 5, 6. Okay, so it says, we're looking at these. If angle 5 and 6 added together equal 90 degrees, then 5 and 6 are complementary. Is that true? So if 5 and 6 added together make 90, then they're complementary. Is that a true statement? Why?
Because it equals 90 degrees.
And how do we know that it equals 90 degrees?
Because they're added together.
Because we added it together. But what is the word complementary? It's the definition of complementary. Complementary means two angles added together equal 90. So if they are added together to equal 90, then they're complementary because of the definition of complementary. Because that's what complementary means. Okay, so that's as hard as these are. Just explain, why do you know they are? Because that is what complementary means. Okay, okay. If angle SWR, which I didn't label, is a right angle, then SW and WR are perpendicular. Basically, did I give you one right angle? Yes. Okay. Does that mean that these are perpendicular? If one angle is a right angle, are the other lines perpendicular? Yes.
Yeah.
Yeah, because if one angle is a right angle and you have two lines that intersect, they are perpendicular because all four of them are. What is that? Definition of perpendicular. Right? That's all it is. You're just stating what's the definition of perpendicular. So I just want you to get an idea. I'm just asking you to think about, why do we know that? Because that's what perpendicular lines are defined as. Okay? Okay. If angle 2 and angle 3 are supplements, then angle 2 is congruent with angle 3. If angle 2 and angle 3 are supplements, that doesn't make any sense. If angle 2 and angle 3 are supplements of RWS, then angle 2 equals angle 3. Oh, of RWB. Okay, so they're saying if this is supplemental with this huge area, this angle that goes from here down to here. So if angle 2 is supplementary to that, and 3 is supplementary to that, are these two equal? Think about that for a while. So let me draw a little bit different picture. What they're trying to say here in this problem, so it's easier to see, if this is one angle, that's the R whatever. This is angle 1, this is angle 2, or no, this is 2, this is 3. This is your big angle. It says 2, let's call this, for right now, 8. And 8 is the whole angle there. Okay, does that make sense? I could kind of take this one out so you don't see it. And so that's the angle that we're looking at. Okay, so if 8 and angle 2 are supplements, and angle 8 and angle 3 are supplements, then angle 2 and angle 3 are equal. Is that a true statement? angle 8 is supplement and angle 2 are supplementary, angle 8 and angle 3 are supplementary, are angle 2 and angle 3 the same?
Yeah,
Why?
because they're both added to angle 8 to make the same answer.
Yeah, when I add these, angle 8's gonna stay the same, right? So if I add these two to get 180, and these two to get 180, because angle 8's the same in both cases, 2 and 3 has to be the same, because they're gonna equal 180. So that's why they are equal, okay? It's actually a betweenness thing, or you can say definition of supplementary, because you're showing that they equal 180, so that would be 2. But it's because they're supplementary, and if two things are supplementary to the same angle, then they are equal. Okay, so that's something that we can look at. Okay, the next one is if AWC, so that's AWC is the right triangle, like here. Is that what it says? AWC? AW's. Oh, W's in the middle. Okay, that's the right angle. Is equal to AWE. It's the same thing we've already done. Never mind, I'm not going to ask you that question because it's ridiculous. It says if this is a right angle and this is a right angle, are these perpendicular? Yes. Well, it says if these two are equal, are they perpendicular? Yes, because the only way we know these have to be at 90-degree angles because one's going straight up, one's going straight across. So they have to be perpendicular. Okay. Okay, so we're going to take a break right now. 5-minute break. Okay. We'll start up again at 9:30.